Dear students, welcome to the session. Today we are going to discuss one more combinational circuit, which is comparator. The name itself, it says it will compare two binary. It will compare two binary numbers. But each binary number may have many bits, right? It may be 1, 2 or 4, many bits, right? So the purpose of comparator is what? It will compare the binary numbers. But based on bits in each binary number, this comparator is classified into 1-bit comparator and 2-bit comparator and 4-bit comparators. Okay, fine. Now we know the inputs for this. Means here we are giving two numbers. Let's take A and B. Then we will compare with comparator 5. Then what are the expected output for this two numbers after comparison? Just see, there is a possibility of these two numbers may be equal, right? So this is one output. When we are comparing two numbers, we may get both are equal. That is one possibility. The second possibility is there is a chance of A may be greater than B, right? That is the second possibility. Similarly, there is a one more possibility that A may be less than B, right? So, if you are comparing two binary numbers, the possible outputs are either maybe two numbers are equal, or one number is greater than other, or one number is less than other. Now, for each output case, we need to find logic expression. For the three cases, we need to find the logic expression. Once you will get the logic expression, then we can develop a logic diagram by using your basic or functional gates. Okay, this is the way to develop a comparator. This is the way. In this way, we can design comparator circuits. Okay, first we'll discuss 1-bit comparator, then we'll see 2, and then we'll discuss 4-bit comparator. Right. As I said, comparator compares two binary numbers. I'll consider two binary numbers are A and B. Okay. Here it is single bit, means A is a single bit number, B is a single bit number, right? So this is my input, which we need to compare A and B. Then possible outputs are what? These two numbers may be equal. So that is first possibility. And second output is what? A may be greater than B. And third output is what? A may be less than B. So for these outputs, we need to find the logic expression, right? So I'll see when we'll get A equal to B condition. So condition for A equal to B is I can say that if A equal to 1, if A equal to 1 and B equal to 1, if A is 1 and B is 1, then we can say that A equal to B. That is one possibility. Or there is one more possibility that if A equal to 0 and B equal to 0, then also we can say that A is equal to B. So to satisfy this condition A equal to B, two possibilities. Either A may be equal to 1 and B may be equal to 1. That is one thing. Or else A may be equal to 0 and B equal to 0. Now, I will convert this sentence form into a logic expression by using SOP forms. So A1 and B1, and I can consider that A and B are high as it is OR. I will consider it as OR gate or with OR symbol. A is 0 and B is 0. So 0 means I can consider it as complemented form. So A bar and B bar. Right. So this is the logic expression for condition A, which is what? A equal to B. Similarly, I will develop the logic expression for the next case. That is, B case is what? A greater than B. A greater than B, directly we can say that if A is 1 and B is 0, there is no other option. If A is 1, directly we can say that A is greater than B. So for this, we can write A value is 1, right? So A I will consider in uncomplemented form and B is 0. So B I will consider in a complemented form. So this is the logic expression for the second case. Okay. Now, third case is what? A less than B. A less than B possibility is what? If A is 0 and B is 1. Right? A is 0 means obviously you can say that which is less than B because B value is 1, right? So, now the logic expression is what? A is 0. So, consider in a complemented form and B is 1. So, uncomplemented form. Now I know the logic expression for all the cases. Once you know the logic expression, then we can develop logic diagram, right? So today, to develop the logic diagram, I am considering all possible inputs. Here the inputs are A and B, uncomplemented inputs, and I will give this input line A to a NOT gate so that I can get A bar. Similarly, I will give this input line B to one NOT gate so that I can get B bar. Right? First we will develop A equal to B function, which is what? AB means A and B is given to an AND gate. A, B is given to an AND gate. And next one is what? A bar and B bar is also given to an AND gate. A bar and B bar is given to an AND. And these two terms are ORed together. So give it to an OR. So that we'll get, this is AB function, this is A bar B bar B function, AB plus A bar B bar, which is nothing but A equal to B condition, right? The next condition is what? A greater than B. For this, the logic expression is A dot B bar. So I am taking input from A and B bar. So give it to one AND gate. So you get A dot B bar, which is nothing but A is greater than B condition. Right? The last condition is what? A less than B. To get this, condition is A bar dot B. So I am taking input from A bar and B, give it to one AND. So we will get A less than B. In this way we can develop, we can design 1-bit comparator. Now we'll discuss 2-bit comparator. Now the comparator purpose is what? It will compare two binary numbers. Right? Let's take the two binary numbers are A and B. Fine. But as it is 2-bit, each binary number is having 2 bits. So A is having 2 bits are A0 and A1. Similarly, B is also having B0 and B1. Right? Here A and B are the two binary numbers, which is our inputs. And each binary number is having 2 bits, which we need to be compared. Right? After comparing these two binary numbers, we'll get 3 possible outputs. First one is A may be equal to B, that is one possibility. And second one may be A greater than B. And third possibility is A may be less than B. Right? So, for each possible output combination, we'll get the logic expression, then we'll develop a logic diagram. So I am considering first condition, that is A equal to B condition. We'll see what is the possibility so that A value is equal to B. Right? When it will be equal, directly we can say that if A1 equal to B1 and A0 equal to B0, then I can say that directly A equal to B. Right? Means if MSB bits are equal and LSB bits are equal, then we can say that A equal to B. Right? So as we know the equality function, when A1 equal to B1, you will get a function of A exclusive NOR with B1. Right? Similarly, for this also we will get A exclusive NOR with B0. I'll tell you how it is. If A1 equal to B1 means what? Means we need to consider each case. If A1 equal to 1 and B1 equal to 1, that is one possibility. Or else A1 equal to 0 and B1 equal to 0. If this case satisfies, then we can say that A1 equal to B1. Right? So A1 equal to B1 and B1 equal to 1 means what? We can write A1 dot B1 or means plus A1 equal to 0 and B1 equal to 0. So we can write A1 bar dot B1 dot bar. Now just see this function is what? A1 B1 plus A1 bar dot B1 bar, which is nothing but A1 exclusive NOR with B1. So I am writing directly here. Okay, whenever we will have equality function, then directly we can write if these two functions are exclusive NOR, then we can say that this is equality function. Okay, fine. And the second one is what? A greater than B. When we'll get this condition, I will tell you. Right. So, for the better understanding of this condition, I am assuming if I have two numbers, let's take 25 and 16. Which one is greater? 25 obviously directly. But actually what we'll check? We'll check first the MSB position. Right? So first we'll check the MSB position. So as MSB position is larger here, so we are assuming 25 is larger than 16. So generally we'll check first what? MSB position. That is one thing. Second, instead of this, if I have two numbers like this, in this case what happens? MSB of two numbers are equal. When MSB is equal, then what will check? The next position. So here the next position is what? As 6 is larger, so we can say that 26 is greater than 25. So from this, my conclusion is, if you wanted to check A greater than B, right? See, A greater than B, with A is having two values and B is having two values. For this condition, first we need to check for the MSB. Right? If MSB means if A1 is 1 and B1 is 0. Okay? If A1 is 1, B1 is 0, then no need to check for second bit. Directly we can say that A is greater than B. That is first case. But every time there is no rule that this A1 may be greater. There is a one more possibility that A1 may be equal to 1 and B1 may be equal to 1, like here. Maybe MSB positions are equal. Then what we'll check? We'll check for LSB positions. That is A1 equal to 1 and B1 equal to 1. And along with this condition, it has to satisfy A0 equal to 1 and B0 equal to 0. So then also we can say that A is greater than B because MSBs are equal. And in the LSB position, A0 is 1. So A0 is larger. So this number is larger number. These are the possible conditions to get A greater than B. Right? Till now I have considered only a sentence form. But we want this in a logical expression. So I will write logical expression form. A1 equal to 1 and B1 equal to 0. So I can write it as A1 and dot B1 bar. The first sentence is over. Or. So I am using or expression here. Now you just see this one, which is what? A1 equal to 1 and B1 equal to 1. As I already told you, if both are equal, directly we can represent that function with exclusive NOR. So I can write A1 exclusive NOR with B1. Right? And here we have one more function. What it is? A0 is 1. A0 is 1 and B0 is 0. So I am taking this complement. So this is a logic expression for A greater than B. Right? Now we will find logic expression for A less than B. Third case is what? A less than B case. This is also similar to second case. Okay. A less than B means we need to check A1 A0 must be less than B1 B0. So here also what we'll check? First we'll check MSB bit. That is, if A1 equal to 0 and B1 equal to 1, then as MSB is 0, here 1. So without checking the second bit, directly I can say that A is less than B. This is one possibility. Okay? Or second possibility is what? Maybe A1 equal to B1. If that is the case, we need to check for the LSB bit, means the next position. So if A1 equal to B1, and what will check? Then A0 must be 0 and B0 must be equal to 1. This is the condition to get A less than B. So this condition now we need to write in logic expression form. So I can write A1 0. So A1 bar B1 or, so with or, A1 equal to B1 is nothing but A1 exclusive NOR with B1, right? And A0 is 0, so bar, B0 is 1, so B0. This is logic expression for A less than B. Now we know the logic expression for A equal to B, A less than B, and A greater than B. Once you know the logic expression, then we can develop the logic diagram. We'll develop the logic diagram here. As we are having 4 inputs, so finally the logic expressions for each case. I am considering here A equal to B, the logic expression is what? A1 exclusive OR with B1 and A0 exclusive OR with B0. For A greater than B, A1 B1 bar plus A1 exclusive OR with B1 and A0 B0 bar. For A less than B, the equation is A1 bar B1 plus A1 exclusive OR with B1 and A0 bar B0. Now we need to develop these 3 logic expressions. Here the inputs are A0, A1, right. 4 inputs A0, A1, B0, B1 and the complemented input I am considering like this. This is A1 bar, A0 bar, B1 bar, B0 bar. Right? Now, first function is what? A1 exclusive OR with B1. So take A1 input. And B1 exclusive NOR and A0 exclusive NOR with B1, B0, A0 exclusive NOR with B0 both are ANDed together to get A equal to B. Right? And the second function is A1 B1 bar, A1 B1 bar and which is ORed with this term, right? Here we require A0 B0 bar, A0 B naught bar this term is ANDed with A1 exclusive of B1. So I am taking this value. Give it to 1 and negate and give these values to 1 or to get A greater than B. See here, this is what A1 B1 bar, this is A naught B naught bar, and this function is A1 exclusive or B1 or B1 A naught B naught bar. Fine. The third function is A less than B, right? A1 bar, A1 bar, B1. Next, A1 exclusive OR function, which is it, and with A1 bar and B naught. Then these two functions are together to get A less than B. Here it is. This output A1 exclusive OR with B1, OR with B1, A naught bar, B naught, and this function is A1 bar and B1. Right? In this way, we can design 2-bit comparator. Thank you.